do an exercise of selection and sizing and selection of hydrocyclones. Remember that hydrocyclones have the are equipment that have the capacity to separate slurries at a certain cut size, where the larger cut size is going to go in the underflow and a lower cut size is going to go in the overflow. So what we have here is a performance chart. Okay, so in this performance chart, what we have is the following. In the y-axis, we have the feed pressure. On one side, it's in kilopascal, and on the other side, it's in psi. In the x-axis, we have the flow rate in cubic meters per hour. And on, well, the opposite scale, but it's pretty much the same one, it's in liters per second. Okay, now this is the feed pressure into the system. Okay, and sorry, this is, yeah, it's feed pressure. It's okay, and this is the flow rate of the slurry, not just the water that's inside the slurry, but the slurry. And then we're talking here about the feed slurry. So these are different, all these trapezoids over here represent, different family models of hydrocyclones, and the number that is between brackets represents the cyclone diameter. Okay, so now the way of sizing these systems is that we enter with the pressure or the feed pressure, the flow rate, we intersect, and there we can find the characteristics of our hydrocyclone. Now, something to take into consideration is that since we are sizing, we also have to take into account the diameter of the system of the hydrocyclone, and depending on that is also controls the hydrocyclone model that we can select. So now we're going to do. I'm going to pause this a bit. Okay, so now we're going to develop a small exercise, and here I'm going to show you the equations that we're going to use for this, and and that would be it. Okay, so the exercise says the following. A flow of 350 cubic meters of slurry, and by slurry I mean water and mineral, that has a specific gravity of 3.2, containing 25% solids in volume, is fed to a bank of hydrocyclones. The maximum allowed pressure difference or pressure drop is 60 kilopascal, and the target overflow is 80%, passing 75 microns or micrometers. So I have two questions here. The first one is to determine the hydrocyclone diameter, and the following is to select a hydrocyclone model and the number of units. Okay, so to start off here, first of all, we're going to use a series of equations, as you can see. Okay, and all of these equations is part of the typical procedure. Yeah, okay, this procedure was established by these experimental or empirical equations, and this was established by, I'm going to write them down over here so you know, Mueller and Joule, or Joule, I don't know how to, and it's a procedure established in 1980. Okay, so there are different equations, and they all lead up to the calculation of the hydrocyclone diameter. So the first equation is something called the applied 50% diameter, and it's calculated as 1.25 times P80, where P80 is what passes a certain cut size. Then we have, with this equation, we calculate something called the diameter, the base diameter, or for the 50 cut size, or the 50% cut size, and this is an empirical formula as well, calculated as this diameter over here divided by three factors, C1, C2, and C3. Now C1, or each one of these has its own formula. This is the formula of C1, where V would be the percentage of volume in solids. Then we have C2, and then we have C3. Now, the delta P here is the pressure drop, and this formula is incomplete. And the C3 factor is 1.65 divided by, this is the specific, this is a specific gravity. Okay, so I'm just going to write SG, okay, not in Greek symbols, but say Calgary, SG of the solid minus the SG of the liquid, and all of that to the power of 0.5. Okay, so we have all the data that we need, okay, because we have the specific gravity, and since it's water, we know that the specific gravity of water is 1. We have the volume percentage, and we have the P80, and we have the pressure drop as well. So I'm just going to highlight the data that we have to use. The percentage of volume, the pressure drop, and the P80. So now we can start replacing these parameters in the formula in order to calculate everything else, okay? So to start off, I'm going to just uncover this. Here, this is going to be 1.25 times 75, which is the P80, or the 80% passing 75 microns. And when we use this formula, the size that comes out here is in microns. Okay. Now, this parameter is going to go in the numerator of the equation, but we still have to calculate C1, C2, and C3. So uncovering C1, that was 1.43, sorry. And I can't see the point, I don't know why. But there's a point there, I don't know why it's not showing. Okay, there it is. So calculating the next parameter over here, this is going to be 53 minus 25 divided by 53, and all of this to the power of 1.43, and that is going to give us 2.49. Now, as for C2, we replace the data, so the pressure drop data, and it's going to give us a value of 1.04. And finally, if we replace the specific gravities here, this is going to give us a value of 0.86. Now, these formulas are built so that the parameters in these units are entered into the equation. So in this case, V is going to be percentage of volume. Okay, so it's just going to be a in percentage. You don't have to put the percent, but it's the value of the percentage. It should be the volume percentage times 100. Well, just leave it at that. Here, the delta P is going to go in dimension in kilopascal units, and for the SG, these are adimensional. Okay. Okay, so now with all of this, we can uncover our final formula, which says that the cut size of the hydrocyclone is going to be 93.75 divided by C1, C2, and C3, and this value is going to come out in centimeters. Okay, so this is going to be the cut size of the amount or the diameter that the hydrocyclone requires for a certain cut size. Okay, and if we pass that to inch, this is going to be the value. Okay, remember that 1 inch equals 2.54 centimeters. Okay, so now with this data over here, going to highlight it in yellow. And this value over here, which is the overall flow rate of the slurry, we're going to go towards selecting the hydrocyclone model and number of units that we need. So remember this number here, which is the 16.6 inch. And let's go down here. So we have three, okay, there's another parameter over here. That's the delta pressure, okay? We are going to assume that the pressure in the outlet of the system is zero Pascal or kilopascal in absolute value. Sorry, not in absolute value, in manometric value, which means that this comes out at atmospheric pressure. I can't remember if it's with atmospheric, it's pH, atmospheric pressure. So in that sense, the pressure drop is going to be equal to the inlet pressure. Okay? Okay. So moving on to that, we have to, here we have to establish some values. So the first value that we are going to establish is the feed pressure. So now our feed pressure is going to be over here. Okay, so I'm going to highlight this a little bit, or make the line a bit thicker. So this is where we have to move in terms of pressure. So apparently all of the models are good for this pressure. And we also have to look at the diameter. Now we have two diameters here that approximate to our the hydrocyclone diameter, which are these two over here, 15 and 20. Okay, so it's better to oversize in this case. So we're going to select this one over here. Let me remove the color here. Sin relleno. Okay. So now what we have to do is select a diameter. Now we have to select, this pretty much is the one that we have to select, okay? But we actually need a certain amount of hydrocyclones, because as you can see, this hydrocyclone can take a feed slurry that goes between, I don't know, 140, and if we go to this other extreme over here, and almost 300. So one hydrocyclone is not going to be enough to process the 350 cubic meters of feed. So what we do here is we sort of, I don't know, we sort of establish a mean value, and with this mean value around here, which would be 150, 175, something like that, 180. With that, we're going to establish how many hydrocyclones we need. So if we go to how this is solved, okay. So our a hydrocyclone diameter calculated according to these correlations is 16.6, and we remember that we approximated that to the highest number available of them available. And then, okay, this is the feed the feed of the slurry. Then the model is this one over here, so at least we have answered what model we actually need. Okay, hydrocyclone model, this is checked. And oh wait, sorry. And the capacity ranges between 140 and, I don't know why I said 300. I know 300 is okay, 290 approximately. Okay, so what we do, we take a central value, which would be the average of these two. So since 350, this is smaller than 350, one hydrocyclone is not enough, so we calculate two hydrocyclones. So if you want to see this better calculated, this would be 350 divided by 215 cubic meters an hour per cyclone, per number of cyclones, hydrocyclones in this case. And in this case, this would give us a little bit less than 2. But okay, so our previous video got cut because I reached a 15-minute limit. I didn't realize I'd taken so long to do this exercise, but okay. So what I was saying is that 2 hydrocyclones are required. And why? Because to calculate the number of hydrocyclones that are required here, I would have to divide the total flow rate, which is the 350, divided by the 215 cubic meters per one hydrocyclone. So in that case, this definitely gives us about 1 point something. Let me calculate the value for you. It doesn't really make any difference because we cannot have 1 point something hydrocyclone. We either we either have 1 or 2. Okay, so in this case we have 350 divided by 215. This is going to give us 1.6 hydrocyclones, which we have to, of course, approximate to the largest following integer. Okay, so that's why we say we require 2 hydrocyclones. Model 500 CV X10 with a diameter of 20 inches. Okay, so I hope that's clear now. And any questions, please let me know if you have any questions.